Okay, we've been playing with some factorizing and using it to solve equations and stuff like that, but this time we'll be finding a way to deal with the case when you cannot factor it nicely, because the numbers are just not going to be rigged for you every single time. So like this guy, it shouldn't take you long at all to see that there is no way you're going to build that 6x in the middle using just a flimsy 2 out the end. So the next best thing is to try and make this thing look as much like a perfect square as possible, even though it's not. So here's what we mean. When we expand a perfect square, we get this x squared plus 2ax plus a square thing. But looking back at our original equation, if we just ignore the constant for now and focus only on the x squared plus 6x, the stuff that carries the x with it, we want that to match up with the perfect square pattern that we have here. So the x squares match already, we don't worry about them. But what we need to look at is a number in front of x. And by matching them up, we see that 2a must be 6, and so a must be 3. So that means the perfect square we're targeting is going to be x plus 3 or square. But to complete the pattern, we need to have a copy of 3 square as well, which is just 9. So return to the original equation. What we're going to do is cheat and slide in a copy of 9, because that's the number we need to complete the perfect square. But we better uncheat immediately, so let's quickly subtract the 9 before anyone notices. And the whole point of that is now this guy we know is the x plus 3 or square pattern that we built. So we can put him here. And then the rest of it is just minus 9 plus 2, which is minus 7. And we have all of this equaling 0. Now this is much better to deal with because we can solve this by normally rearranging stuff. So watch, we can kill the negative 7 by adding it. Then we can kill the square by doing a square root, remembering again to take both positive and negative square roots. And finally, we kill the plus 3 by doing minus 3, and we have our two answers. Minus 3 plus root 7, and minus 3 minus root 7. And the fact that there's a surd at the end is exactly why there was no way to factorize it nicely just using whole numbers. Okay, so let's quickly go over the process of that with this initial quadratic here. The key step to finding that yellow value of a we needed on the right was by matching up the 2a with 6, which meant that to find a, we had to divide the 6 by 2. But because that perfect square expansion pattern never changes, that's always going to happen. So you're always going to find a by dividing the middle number, the one in front of the single copy of x, by 2. So because 6 divided by 2 is 3, we could see we were aiming for x plus 3 or square. And how do you actually build the pattern for that perfect square? Well, you need to slide in the green number, the 9 in our case, which came from squaring the yellow a number that we just found. So we would slide him in there, which is fine, so long as we subtract him straight away. But now we can turn the first part into the perfect square pattern and just see what constant we're left with at the end by just calculating it, and for us it was negative 7. Okay, so it really revolves all around that middle guy. Okay, we halve to see what perfect square you're targeting, and then slide in the square of that number to build the pattern. Okay, and this whole process is called completing the square. So let's see one more example of that process here. So you can see again, you can't nicely factorize this guy, but we now know we can proceed by just looking at the middle number. So how we complete the square here, how we find the number that goes in the perfect square bracket, is we take our 10, which was matched with the 2a from the previous screen. And so that meant we halve it to find the a, so that's going to be 5, and that number will be the number sitting inside the perfect square bracket thingy. Then we square this 5 to see how to build the pattern. Okay, and so 25 is the number we have to slide in. Okay, so some just remember that as halve it then square it, but hopefully you see why. So anyway, we break apart the equation, we slide in the 25 and cover our tracks by subtracting 25 straight away, and there's the perfect square pattern. Okay, so 5 is the number that goes in the bracket. only it's negative 10x, it's minus, so it'll be x minus 5 all square. Then the numbers, minus 25 plus 34 is just 9, and all that equals 0. So we can subtract the 9 to kill it. Then we kill the square by taking plus or minus square root again. But at this point, we see a negative number inside the square root, which when restricted to the real number line is impossible. It doesn't exist on the real number line. So that tells us that there are no real solutions. No real number fits that x in the original equation. Okay, and we'll see later though that this whole process wasn't all pointless. Just because there's no solutions doesn't mean that this is all useless. There is still meaning, there is still value in doing this for things like graphing and eventually calculus. There are things other than solving equations that we actually use this same technique for. So it's good to do it even if the end result is that there are no real solutions. Or if you allow complex numbers, we just have that